We have Irene Zhang, who's going to go now. Irene, this event would not have happened without Irene. So there's a big thank you for just putting this whole thing together. Before she gives her talk about her research that she and many others have been working on recently. She did her PhD at University of Washington. She's worked on distributed systems, mobile devices, cloud servers, is at Microsoft Research now, and has done this really cool work on Demikernel, which we'll talk about. And without further ado, Irene, please go for it.
Thank you. I also do want to thank Zishan too, because I really did not do any work for this event. I simply tweeted, and the PapersWeLove community made this all happen. I also want to thank USENIX. I will start out my talk by thanking USENIX because I wanted to call them out for giving us the opportunity to now have OSDI every year. OSDI is, as we've been talking about, where Bigtable and many really important pieces of work were presented. And it's really fantastic that they're now giving us the opportunity to hold that conference every year, which means we're going to get double the number of great papers out there for people to take a look at. So I'm going to talk about some work that I've been doing recently with a ton of people. I get the unenviable position of following up to Jeff Dean. I pointed out to people that this is much similar to being the act after Beyonce. So hopefully people, will find this work interesting. Demikernel is a new operating system that I've been working on, and it's designed for kernel bypass. So in addition to talking about Demikernel, I'm also going to talk about kernel bypass and some of those hardware accelerators that Jeff talked about before me. So there have been a couple of hardware trends over the last decade that have really driven this work. First of all, we've seen network devices and just I/O devices in general, also disks and NVRAM, have all become faster and faster in sort of a very exponential way. At the same time, Moore's law has not been doing so great. It's kind of plateaued. And so our CPU speeds have not been increasing exponentially along with I/O devices. And this really means that increasingly, when we look at data center servers, the CPU has become the bottleneck. And this is extremely strange because this is something that, 20 years ago, people could not have imagined being possible. It also means that CPU cycles have become this at who is of these CPU cycles, we notice that actually the operating system, which is, a beloved piece of software for me, picking up a lot of those CPU cycles. % is being spent actually in the operating system, not doing application work. This trend has become especially as both applications and network round trips have gotten lower and lower. So, Luis Barroso, who wrote a fantastic paper on tail latency with Jeff Dean, also recently wrote a piece of article for the community of the ACM on how microseconds are really becoming crucial metric for modern data center services. And that means operating systems, they just don't operate at the scale that's fast enough anymore.
Irene, sorry to break in here. Can we have you turn your video off because we're getting a little bit of audio chopping?
Yeah, I think it said my application or my network was unstable, so I apologize for that. Yeah, please tell me if, if it doesn't work or you can't hear me. So one of the solutions that we've come up with recently for dealing with the overhead caused by operating systems is actually a very old solution, which is that since I/O devices have a lot more computational power now, we can go ahead and actually offload a lot of the work that this OS kernel would do onto the I/O device and just get rid of it, bypassing the OS kernel entirely and all of its overhead and letting applications like Redis in this example just directly perform I/O from a user space application. So this sounds great. But kernel bypass today has really a kind of mixed bag of good things and bad things. So there's some really great things about kernel bypass. First, it's really widely available. You can get it at just about any of the big cloud providers, and most modern NICs support it. I guess actually most modern I/O devices support it. It works. We have seen a lot of research systems that have shown that kernel bypass can be incredibly effective at lowering the latency of modern data center applications. However, we found that using kernel bypass is really, really hard. Porting an application is complex. It's also just an expensive investment in terms of engineering time, and it's very difficult to maintain. So what we've seen is that kernel bypass has really been limited to a small set of specialized applications like scientific computing and other kinds of things like that are not really the applications that are being deployed at scale in the data center today. So in the rest of this talk, I'm going to first give an introduction on how kernel bypass works and why it's kind of this mixed bag of good and bad things. And then I'll talk about Demikernel and how we're going to try to make kernel bypass much, much easier to use for general purpose data center applications. So in order to understand kernel bypass, I'm going to use hardware virtualization as an example. And the reason is because hardware virtualization has, in contrast, been a really, really successful technology. It's used everywhere. It saves tons and tons of CPU cycles every year, and people really love it. And so what we're going to do is we're going to play kernel bypass Mad Libs, which is like the world's worst word game. So in order to understand how kernel bypass and virtualization are related, I'm going to explain how virtualization works and then talk about the kernel bypass equivalent. So with hardware virtualization, the I/O device is allowed to bypass the hypervisor, and the I/O device provides that hardware support so that the virtual machine can directly issue I/O. This means that the I/O device has to have an I/O MMU that's capable of address translation from guessed physical addresses to lower level machine actual physical addresses, so that the I/O device can actually directly go and grab memory out of the virtual machine. And widely deployed technologies for virtualization include SRIOV. Okay, so what does this look like when we switch to kernel bypass? Well, we basically just move everything up a level. So in kernel bypass, the I/O device bypasses the OS kernel, which means that your application process is able to directly issue I/O instead of your virtual machine. And then your I/O MMU translates from virtual application level, user level addresses to the very lowest level physical machine addresses. And widely deployed kernel bypass devices include DPDK and RDMA. So hopefully that gives you a better idea of how kernel bypass technologies let application level, user level processes directly access I/O devices safely. It really is similar in a lot of ways to hardware virtualization. And in fact, in Arrakis, which was published in OSDI many years ago, we showed that you could actually use hardware virtualization technology to support kernel bypass. So why hasn't kernel bypass taken off as quickly as hardware virtualization? Well, unlike hardware virtualization, the operating system kernel does much more than just multiplex hardware resources, right? When you look at a virtual machine, your hypervisor is just providing it with a virtual NIC because there are more than one virtual machine running on the server. Well, what does your operating system provide to application processes, right? Well, it doesn't just provide a virtual NIC. It provides, a TCP stack. It provides sockets. For storage, it provides a file system. And so these things are all actually really hard. And so let's take a look at what happens when we move to kernel bypass, where devices are supporting the operating system kernel instead. So we're going to take a look at networking because that's the most widely used kernel bypass technology and probably the one that we've taken a look at the most. So when we look at the architecture of a modern operating system, right, you have your application, it runs on top of an OS that's providing lots of features. Well, when we move to kernel bypass, we move those features onto the IO device, like address translation and device multiplexing. But the IO device is not actually capable of supporting everything that your operating system does. In particular, it's not providing any sort of higher level abstractions. It doesn't have TCP on it. It's not supplying you with sockets and lots of other things that the application would expect or need to use. So then what do? Well, there's sort of this gap here that, we don't know how to fill. One option, which is the one that we've currently mostly taken, is to build your own custom sort of networking stack, essentially. Just roll your own messaging layer. So that's pretty hard and kind of unsustainable if every application has to build their own networking layer. So another option that people have suggested is to just reuse the operating system networking stack and move it up to user space. Unfortunately, what we found is that that's not actually fast enough for kernel bypass devices because traditional operating systems aren't built to work with microsecond level NICs. So then we take a look at other stacks that actually have been explicitly built for kernel bypass. So MTCP, for example, implements a TCP stack in user space, and it offers sockets and an interface that's exactly the same as POSIX. Unfortunately, MTCP is completely oriented towards throughput. And when we tested it, we found that its performance was actually slower than going through the Linux kernel. So right now, application programmers are pretty much stuck. They just don't have a whole lot of options if they want to actually deploy a kernel bypass application. And it gets a little bit worse. Kernel bypass, unlike hardware virtualization, has been really complicated. And it's been complicated by the fact that devices can't seem to agree on what operating system services they should actually provide. And in part, this is due to the fact that different devices have different sorts of capabilities and hardware available. So you've got RDMA NICs, which are incredibly capable devices. They provide a lot of the stuff that an operating system would. However, they depend really heavily on the network to do things like congestion control. And so that makes RDMA really hard to deploy. On the other hand, DPDK basically does the hardware virtualization thing of providing a virtual NIC and nothing else. Unfortunately, DPDK is really simple, but it means that you have to spend a lot of CPU cycles running a full networking stack in user level. So we think that coming down the pipeline, there are probably going to be even more programmable devices. And unfortunately, we don't know what the interface of that is going to look like. And so what application programmers have to deal with today is this completely non-uniform API and architecture that they have to try to reason about and build an application for. And usually if they commit to some kernel bypass technology, they're not going to get to use anything else. Even worse, we don't know what other applications, what other devices, kernel bypass devices might be coming down the pipeline. And so there's actually no way to future-proof your application either in case, we stop supporting some of these devices and start supporting other things. So overall, the world of kernel bypass is kind of very hard to navigate today for application programmers. And so when we started the Demikernel project, we really wanted to change that. So I'll talk first about what Demikernel is and how it's designed to help application programmers with kernel bypass. And then I'll go into more of the guts of Demikernel. So the Demikernel at its very core is a kernel bypass OS. It's an operating system designed to support applications that use kernel bypass IO. However, because it's kernel bypass, we can't really call it an operating system in the traditional sense, perhaps, because many times people would define operating systems by their kernels. So instead, I have called it a kernel bypass OS architecture in the vein of exokernel or multi-kernel instead. Demikernel has a couple of design goals. The first is to completely standardize the kernel bypass API and standardize it in a way that is separate from the kernel bypass hardware itself. The next one is to offer an architecture that is flexible enough to support devices with different OS features, but still provide a uniform experience for application programmers. So we don't want application programmers to have to worry about the hardware-software divide of their kernel bypass device. We want them to think that everything looks the same from the top. But so then we need an architecture that's going to accommodate these differences between the devices. And then the very last one is that these new kernel bypass devices absolutely demand single microsecond I/O processing. And so from the very beginning, we've built Demikernel with that in mind, that the I/O device is going to be incredibly, incredibly fast. And whatever we do in the operating system, it cannot add any more overhead than single-digit microseconds. Okay, so what does Demikernel look like? Well, Demikernel fills that question mark space, the big question mark that was in my original slide. It lives in the space that used to be filled by an operating system. However, it shares the same user level process. So in that sense, it's a library. So that's why we call Demikernel really a library OS. However, it only lives on the data path. Oh, sorry. So it lives in user level, but it provides OS level services. So all of those things that we talked about that were missing from the kernel bypass device is going to be provided by a Demikernel user level LibOS. But it only lives on the data path, so it's only providing these features and services for the critical I/O path. And it still relies on the standard OS kernel for control path operations. And so this is why we call it a Demikernel, because it's a little half kernel. So Demikernel is not just a single library OS, however. It's actually a collection of libOSs, one for each type of kernel bypass device. And so the idea is that you would have a custom kernel bypass libOS for RDMA, for DPDK, and for whatever your programmable, new SmartNIC is. This means that the application is able to see a single unified interface and architecture. It also means that whatever new hardware is coming down the pipeline from hardware vendors, we don't have to worry about it. We can just continue to build new Demikernel libOSs to support them, and our applications will be able to smoothly transition onto them. All right, so now that we've talked about sort of an overview of what Demikernel is, where does it live, and what it does, let's talk about the Demikernel API. So this high-level unified API for kernel bypass is very, very important to how we're going to provide ease of use for applications. When we were designing the API, we had a couple of features in mind that were really crucial to matching the set of design goals that we had for the Demikernel. So the first one is that instead of having queues for I/O, instead of having sockets with read and write for I/O, we use queues with push and pop operations. All of the operations are asynchronous by default and return a queue token so that you can block on completion if you want. And then we provide this wait interface that you can use to interact with queue tokens and wait for your completed asynchronous operations. And then finally, the entire interface is designed to be natively zero copy, that any application built on top of Demikernel should be aware of zero copy, and it should be designed for a zero copy I/O API. Okay, so I'm going to go through a couple of slides explaining each of these features. So the first and most important part of the Demikernel API is that we replace files and pipes and sockets with queues. So we expect each operation that you do to a queue to be an entire I/O. So one of the difficulties with using a pipe-based interface is that the OS doesn't know when it should actually issue the I/O. So instead of having reads and writes, the Demikernel queues use push and pop. We also provide an in-memory queue that's very similar to a Go channel. And then we expect applications to submit using a scatter-gather array, an entire I/O at a time. So an application should never write a header and then later write the payload for a packet. All of that should come together so that to minimize latency, the demikernel LibOS knows exactly when to submit the I/O. Okay, so as I mentioned before, all of the operations to demikernel queues are asynchronous. So there's really just push and pop. They're asynchronous and they return a Q token. And that Q token refers to a specific I/O event. Then we offer a new wait interface, which can block on one or more I/O operations. And so you hand it one or more Q tokens. And these Q tokens are tied to specific I/O operations that you're blocking on and waiting to complete, not specific interfaces or devices. So we don't have the POSIX epoll interface because we don't want threads all waking up and then racing to read on socket. We want threads instead to explicitly be waiting on specific I/O operations that they're going to then work on. And this lets the LibOS have a lot more fine-grained control over how application work is scheduled because it can control when and where it delivers each I/O operation. Okay, so let's separately look at push and pop and what that means when we talk about zero copy. So I said earlier that demikernel has a zero copy I/O interface. As we'll talk about in the next section, not every LibOS actually uses zero copy, but we assume a zero copy interface because that gives the LibOS the option to use zero copy when it makes sense for latency, or in fact is critical for latency. So the zero copy semantics of the demikernel queues are that pushing a buffer gives ownership of all the scatter-gather array elements to the LibOS. So until the Q token returns, the application should not modify the buffer because the LibOS might still be using it. The only sort of small wrinkle or difference to this is that we actually provide use after free protection. So we found that a lot of bugs were being caused in applications by use after free, and that we could actually provide use after free protection pretty easily. So that means for applications that push data into a scatter-gather array for I/O, they can actually then immediately free those buffers and not have to worry about writing to them later because they freed them, or actually freeing them later. And so this works really, really well for applications that don't update in place. So for example, if you have a Redis key and object, and those objects are different sizes, so you're not going to overwrite an existing object with a new one, then this works really well if you know that you don't need the buffer after you push it for I/O. Okay, so then the semantics for POP, the demikernel LibOSs allocate and manage all buffers for incoming I/O. So this is designed to simplify applications, but it also means that the LibOS is allocating buffers and then passing them immediately back to the application. So when a POP returns or a wait returns from a POP Q token, it'll return with a scatter-gather array of buffers for the incoming data, and the application now owns those buffers. Then the application is responsible for freeing those buffers when it doesn't need them, and the LibOS will reuse them later. So to summarize the demikernel API, I'm going to show what a standard demikernel application looks like when it's in a processing loop. So essentially, almost all demikernel applications that spend most of their time processing network I/O will start out by popping. If there's nothing to read, if there's no incoming I/O, they'll get a Q token, and then they'll wait on it. When that wait returns, a scatter-gather array will come back with the incoming request. The application will parse and process the request and possibly push a response. And so basically, this is the programming pattern for almost all the demikernel applications. We expect them to mostly be performing I/O a lot of the time. just for a quick comparison, I'll overlay on top of this what happens with POSIX. It's a lot more complicated. The POSIX API has some things that I think everyone understands are not ideal for I/O processing. And so part of the goal of the Demikernel API is simply to fix those problems. All right, okay, I think I have to move faster. So now that we've looked at the external facing parts of Demikernel, let's take a look at Demikernel LibOSes. I'm going to talk about how they're designed and built and some research challenges. So Demikernel LibOSes can actually be designed in any way because their really only requirement is that they provide the Demikernel API on top of a kernel bypass device. However, as we've been building Demikernel LibOSes, we've used some general principles for minimizing latency and making sure that we get the best performance and that we're able to provide the features that Demikernel requires. So first, Demikernel LibOSes share execution threads with the application. Next, we use coroutines as our core unit of work and scheduling for OS tasks. And then finally, almost every LibOS integrates a co-designed memory allocator. So I'll talk about each of these in more detail. So like Arrakis and some other of the kernel bypass operating systems, Demikernel shares or interleaves operating system processing with application processing. So this is really critical for minimizing latency. It also lets us control scheduling at a much finer grain. And so compared to other systems like Snap, which schedules OS work on processes, or MTCP, which schedules it on threads. In those cases, you're probably pretty much leaving it up to the operating system to decide how to allocate time and cycles to the OS versus the application. Whereas in Demikernel, we're able to make that decision ourselves. However, because we don't have interrupts or other things, the application needs to be cooperative. It needs to frequently enter the LibOS, and it has to either call I/O or be in wait and explicitly giving CPU cycles to the operating system. Otherwise, we won't be able to perform background tasks like doing ACKs for TCP if the application's not regularly performing I/O. But we don't expect this to be a problem for most applications, for example, ones like Redis, because essentially they're sitting there idle when there isn't any I/O. They're mostly just responding to I/O. Okay, so in order to do this really lightweight multiplexing of OS tasks on application threads, Demikernel uses coroutines. So we could build a LibOS as a giant monolithic single-threaded thing, but that makes it really hard to actually decide what work to do and when. So coroutines are what we use to let us multiplex OS tasks and make a decision about whether we're going to do packet processing next or run a background task or actually return to the application. Our coroutines are implemented just with the standard coroutine libraries for C++ and Rust. And we have a Demikernel specific scheduler that knows which coroutines are runnable and which ones have yielded but need to run again in the near future. So kernel bypass scheduling is something that there's been a lot of research work done on. But in Demikernel, we actually ran into a lot of challenges that I feel like existing papers have not tackled. And we've answered some of these questions. We haven't answered some of them, and some of them we haven't answered to our satisfaction. So they include things like, how many cycles do you give to the OS versus the application if you have really fine-grained microsecond ability to make decisions about this? And if you have to make those scheduling decisions, how do you actually make them fast enough when a packet shows up? Do you decide to immediately enter into packet processing? Do you do some background work that you have been waiting on doing? Or do you do the packet processing and then go to the application and then wait for it to return to you again? And you have to make all of these decisions very, very fast. And so I'm not going to go through all of these questions, but I think there are a lot of interesting research projects that could be done based on these problems, and if you just dug a little bit deeper. So the other thing that's interesting about demikernel LibOSes is that almost every one of them uses a custom co-designed memory allocator. We currently are using Horde because it's an extensible memory allocator. And so we're able to use Horde, for example, to implement use after free protection by keeping a single bit for reference counting. It also lets us do transparent zero copy by supporting whatever method the kernel bypass device has for registering or otherwise finding memory for I/O. So kernel bypass devices need to be able to do translation from virtual addresses to physical addresses, which means that they need to have some idea of where the buffers are located. So for example, in RDMA, they do that with registration. And in DPDK, they do that by using specific memory pools. And so with Horde, we're able to, under the covers, actually make sure that we register or use memory from DPDK's memory pool. So this is an area that I think has even more interesting implications for what does it mean to have a kernel bypass aware memory allocator. Buffer management in general is really hard when you're running microsecond I/O. And so I think more support for applications needs to be done in order to help them with just simply managing the large number of buffers that they have for incoming I/O and outgoing I/O. Okay, so I've talked a bit about demikernel LibOSes and the design challenges and interesting research problems that are there. So let's just take a really quick look at some numbers. Basically what we would like to know is if you move your application to demikernel, what do you get? So our evaluation we did with a very simple RPC echo server. We have two versions. One is implemented on top of the POSIX API and goes through with the Linux kernel. The other one is implemented with the demikernel Q API and goes through demikernel LibOSes. We ran the experiments on both a cluster that we have at MSR as well as some Azure VMs. And then we've implemented right now, roughly speaking, 3 demikernel LibOSes. So the first one is one that just implements the demikernel API on top of the POSIX interface. This is for testing and for baseline measurements. It makes it so that if you don't have access to kernel bypass devices, you can still run demikernel applications. Then we implemented LibOS for RDMA. We actually built 2 of these. One is for the Linux IB verbs interface, and the other one is for the Windows ND-SPI interface. And then finally, we built a DPDK LibOS that uses a custom user-level TCP IP and UDP engine called Catnip, which we've built from scratch in Rust. So here are the latencies for essentially running a round-trip echo on Linux or various kernel bypass devices. Across the bottom, there are the different demikernel LibOSes that we used, plus on the very left is the Linux baseline. And then the latency is given in round-trip time in terms of microseconds. So when you move an application to demikernel, if you have access to kernel bypass hardware, you're going to get up to a 5x reduction in latency. Catnip is able to provide TCP with single microsecond overhead. This was definitely one of our goals. We wanted to be able to support a general purpose algorithm on top of DPDK, which does not give you a lot in terms of hardware, but still provide that with very low overhead. And so as you can see, if you have access to RDMA, then that's great. You can get better performance. But because RDMA is so hard to manage and it's so hard to get access to the hardware, you can just move your application to DPDK if you don't have that available. And that doesn't require any code changes because the demikernel API makes applications portable across all 3-4 of the bars on the right. So moving to Azure, Demikernel is also able to provide a big performance boost in the virtualized environment. So if you're running Linux and you move to Demikernel, we're able to leverage the DPDK hardware that's available on Azure and actually get you a 4x reduction in latency. The Demikernel LibOS that actually goes to the Linux kernel doesn't perform quite as well. It's implemented using polling on reading the socket. So yeah, the performance seems to vary quite a bit there. But the DPDK performance is always reliably good. So if you have access to DPDK in your VM, then you can run it with DPDK. And if not, you can always fall back to running it through the Linux kernel. Again, this portability is really important because it means that we can move applications that might have been built for raw kernel bypass hardware onto cloud servers without having to change any of the code. Whereas if you've built your application for RDMA, right now it's very, very hard to be able to deploy an RDMA application actually virtualized on a cloud platform. So finally, the Windows latencies, as I mentioned, we built a Demikernel API, Demikernel LibOS for the Windows RDMA interface, which is called NDSPI. It significantly reduces latency for Windows, partially because our baseline is based on WSL, which might not be accessing the Windows kernel as efficiently as it could be. But I think what's really important to note here is that this is actually the exact same TCP echo application that we've been using the whole time. And we're able to run it on Windows and Linux, on Azure and on bare metal. And so the amount of portability that you're getting from the Demikernel API is very impressive here. And of course, the RDMA numbers are also impressive themselves. Okay, so to wrap up, I've talked about Demikernel. It's designed to be a low latency kernel bypass operating system architecture. It provides a portable API and a flexible architecture through a series of kernel bypass libOSs that are designed to work with different kernel bypass devices. And finally, I just want to say that I think in this world of kernel bypass OS design, there are a lot of interesting open problems. And I'm really excited to see what operating systems work will occur there, because I think it's a place where there's going to be a lot of innovation in the next decade. Thanks, everyone.
Thank you, Irene. That was great, actually. Slides are very dope. Oh, we got questions. We got a few questions rolling in. So I'll start with those. Let me turn my camera on. David Ashley tells me. Okay. We can, if you want to put, we don't see you though. Maybe we can see you on video now.
I'm trying to figure out how to do that. Okay. Okay, great.
And you didn't show your high heels. I guess you have your high heels in the background too. We have those. All right. So
more importantly, the cats are here.
The cat.
More importantly,
wow,
the cats are here. So that's clearly. He slept through the entire talk. I think he wasn't too impressed.
The cat's doing Adrian's hours, like late night and night hours.
Yeah.
Okay. All right, we have some questions in the chat. We'll go with those first. So somebody else said, "Go Chrissy Teigen." Did I miss the Chrissy Teigen thing? I don't. I might have been lost on that, but oh, they're calling you Chrissy Teigen. I got it.
Yeah, it's Christina's fiance.
All right. So question, if I correctly understand, Demikernel is a library that is linked with a program to bypass OS syscalls, living on an existing OS such as Windows or Linux. If so, how can Demikernel interact with resources such as sockets without transitioning into the underlying operating system?
So if you look at technologies like RDMA or DPDK, those libraries are giving the user level process direct access to the hardware NIC. So that's why we're able to directly send out packets on the network without transitioning through the OS kernel, because those hardware devices have the capability of letting us safely access the network device.
Yeah, it's good. Maybe we can gather some links to after this. I think some people who are not familiar with DPDK and things would probably be pretty good to know, like some of the history on that too. We could do that. Okay, so another question is, do you think it is feasible to implement the POSIX API on top of Demikernel's Q API? And do you think one should, given the fact that POSIX is, for lack of words, I guess, lacking?
Yeah, so I think it would be not that hard to do the POSIX API on top of the Demikernel API. You'd have to make some design decisions. For example, when to push. Whoever is building that would have to make a decision about when to actually issue the I/O. But yeah, I think that could be a great way to sort of slowly move applications onto kernel bypass. That you'd have something that was maybe not optimal or the best performance, but you'd still be getting something that is very good.
I think you're getting tweets in the background. We have more questions.
Yeah,
does Catnip currently do congestion control? It's a library that you brought in over and you did in Rust, but does Catnip currently do congestion control? Does it do something like DC TCP?
It does not currently have a congestion control implementation. I think, we've been talking about working on it. One thing that we thought about doing is, I think Mohammed and some folks from MIT did an extensible congestion control module that is in Rust. And we've talked about porting that or putting it into Demikernel or into Catnip, which would allow us to use all of the algorithms that they've implemented inside that. Cool. I forgot the name of the system.
There's so many names. So we have one internally in our PWL channel. Someone asked, because you showed the example with the numbers that you're running for round trip time, and you had like the echo example. But I guess someone had the question, which was, you showed Redis in the opening slides. Do you have an example where you have like an application working with Redis kind of working in this thing? Or maybe the question really is, do you have other applications that you've done evaluation on, either in the paper? Obviously, the workshop paper was a couple years back or a year back. I mean, so do you have like other applications that you've kind of tried this on?
Yeah, so we do actually have a ported version of Redis. If you go to the GitHub repo, it's there in, I think, a submodule, and you can run it yourself. I've run it. I think we have not run Redis on the most recent version of Catnip, which was why I didn't show the Redis numbers. But yeah, you can download it and run it yourself.
The awesomeness of open source, right? Right there. So
yeah, exactly.
Okay. Yeah. All right, more questions. We got somebody asked, and they clarified this could be they say a stupid question, we'll just let it go, which is, could kernel bypass help with my container to host compatibility issue with like machine learning acceleration cards, GPUs, ASICs, FPGAs, etc.? Just thinking if the container was given direct access to the hardware via kernel bypass, they would no longer have to match the driver version of the host OS. And maybe Demikernel could help with this.
Yeah, so first of all, not a stupid question, and by far, actually a very complicated one.
Pretty good question. Yeah, very, very deep.
Yeah. So I think there's no reason kernel bypass wouldn't work with containers. However, you do still need a user level driver to talk to the device. So it's not there's no free lunch. We spend a lot of time messing around with user level driver versions for the Mellanox NICs we have, trying to match them to versions of DPDK and figuring out which work the best, which ones don't work at all. And so you honestly are still essentially running and building an OS. You have the same OS problems, except that they're now just visible to your application because they live in the same address space. More visible.
Good answer.
More visible, I would say. Yeah.
Yeah. So we have a question from somebody named themselves Rodrigo Fonseca, who said, how do you see these primitives extending to the network and to a distributed context, especially if the application is running on 2 demikernels? For example, the network would know about the boundaries of messages, possibly.
Yeah, so we actually, right now, demikernel is kind of a mixed. One of the things about demikernel is that you can have libOSs that are pretty customized. And so we actually, the original demikernel libOSs had framing for TCP. So for UDP, if things fit in a packet, we can just send them as a packet and you can receive them as a packet. And that's great. But for TCP, you don't, you might not know where a message starts and ends. And so we actually can put in our own framing if both ends are demikernel. That means that, you can build like an RPC service where this is the whole RPC. I don't need to wait for more of it. I can parse it like this. The other thing that we've talked about is building demikernel libOSs that know how to do that framing for like HTTPS or like REST or JSON or something like that. So like more user level aware libOSs. Yes, also Rodrigo is in my group at MSR and he should just talk to me offline about this.
Yeah, I mean, it's a good question because I've done some work dealing with jumbo framing. I mean, it can be complicated. There are ways to do things where you add a complication. So it got more like an evaluation question that came up, which was, what happens as the payloads increase in size? I guess I'm running various benchmarks if you've seen.
Yeah, I mean, latency goes up a little bit, throughput goes up. If you have bigger packets, you get better throughput. Yeah, I don't think there's anything particularly like unexpected there, I guess. So far, actually, Sujay could answer this question. I'm not sure if we support larger than jumbo frame UDP packets and stuff. And so we've done testing pretty much up to there. But then if you use RDMA, you can get up to 1 gig because it's using segmentation offload on the NIC. And so, yeah.
Are you saying it uses hardware level segmentation? Okay.
Yeah, that's right.
Yeah, so RDMA will do that. Yeah, but for DPDK, we have to do it by hand. And so that depends on whether Catnip implements it, which I don't remember.
Yeah, not at the moment.
Okay, yeah,
so
right.
I knew that with DPDK. So right. So we have more questions. Actually, Ada, I could have maybe Ada should have asked it here maybe, but I can ask it. It's on the chat, which is she'd very much like to talk. But she said, for the IB case, what was the other functionality that you had to add to libOS beyond the verb user level drivers? You can read this while I read it out loud for the audience. Also, a big challenge that still remains is to migrate applications from a blocking socket-based API to an API such as the async libOS queues. Any comments on what one can do there?
So for the first one, the big thing for RDMA is mostly management of buffers and then implementation of flow control. So RDMA, I guess you can use one-sided RDMA, but we're using 2. If you use two-sided RDMA, you have to manage the receive buffers and allocate them yourself, and yourself being the application. And so the other side can't send faster than you have receive buffer is allocated. Otherwise, the whole thing just crashes. And so basically, we implemented flow control for our RDMA and pacing of the sender so that we could make sure that we had enough receive buffers before they started sending a ton of data our way.
Cool. Cool. Yeah. So we have more. So you mentioned that MTCP performance.
Oh, I forgot to answer the second question. Yeah, the second question I don't have a good answer. Yeah. So, okay. So I guess I mean, so part of the thing that we've also been thinking for Demikernel that would be very cool, but we haven't done yet is integrating it with things like libevent and then like Go, right? So some higher level programming frameworks and some higher level programming languages. So if we were able to integrate it with Go or libevent or, whatever popular programming framework there was out there, then you could port the application to Demikernel more easily. But if it's directly using blocking sockets, we do have a blocking version of our interface, which is basically, calling push and then wait immediately after with the Q token. And so we can support that. It just doesn't perform very well.
Right. Like, what are the big benefits of the end? Yeah, right. Makes sense.
Yeah.
Okay, someone mentioned that MTCP's performance is lacking. You mentioned that in your talk. How is Catnip's design different from MTCP? And do you also use a dedicated core?
We do not. So the big difference between MTCP and Catnip is that MTCP does all of its network processing on a separate thread. And so when a packet comes in, it has to go through network processing on that thread before it's put into a queue for the application to pick up on the other end. And then the same back the other way. And so that increases latency. And it also means that you have to dedicate one core. I mean, essentially, you've got a 50-50 split if you've got one application core and one networking core, right? And I think MTCP kind of expects you to just tune that yourself. I looked at that code. It
definitely does want you to do it yourself.
Yeah. I think one of the reasons that we were getting really high latency was that we tried to put it all on one core. And that means that for every, because it uses kernel threads, it's not using like a lightweight user level threading library. You're actually entering the kernel on every network processing because you're switching between the kernel thread, the two kernel threads when we tried to pin them to the same core. So we should really be using two cores. And so the really fair comparison, we were kind of not doing this was initially we thought we would use MTCP instead of building our own stack. It just turned out not to perform well enough. We couldn't get it to single microseconds. And so, so Catnip is all coroutines and it does the switch super fast inside the coroutines. Yeah,
it makes sense. So another question is, does Demikernel provide isolation among multiple applications that want to access the I/O device? So I guess running multiple applications at one time.
Yeah, that's a really good question. Demikernel doesn't implement isolation, so you need the hardware device to support isolation. So that means either your hardware device, for example, if it's RDMA, multiple processes, user level processes, can safely use the RDMA NIC and share it, and the RDMA NIC will multiplex and isolate the different processes. So for DPDK, it doesn't work that way, but you can use multiple virtual NICs through the hardware virtualization. But right now, all we've tried so far is just taking the entire NIC and handing it to one user level process.
Yeah, I know that well. There's another question. I have one more. I'm gonna ask one from me because I've been working for a year on like a higher level DSL for doing DPDK stuff. Is what this work we were doing at Comcast for other work. But one question I have is, where do you think? So you talk about obviously things like Catnip and these things, and you had that question in your challenges about maybe mapping the Rust ownership model to working with byte buffers and packets and stuff like that in memory. Where do you see kind of the program of the kind of the programmable networks, the programmability kind of stuff working as you go more toward this space, right? Like this is more like a general question on the space, but where do you see attempting to use more high level concepts in this space for that can make it where, like, the joke I always have is that how do we make people who program in React, Facebook React, now able to write network functions? That was our idea. But like, what if even in general now, because you're obviously working to emulate a lot of these like library application level stuff that has been done with OS in the kernel. Where do you see things going from, like, now I'm just like, a programmer who writes in the application space now being able to write in this, do things in this space easier going forward, I guess?
Yeah, that's a really good question. I was hoping that some PL people had an answer. So for the Demikernel, we try to do things as transparently as possible. But to be honest, at the end of the day, if you're writing a microsecond level application, it's just really hard, right? You have to be very careful about how you use buffers, how you, it's just really hard. And so as much as we can, we do things like, use after free protection. But we don't really have good answers for, like passing ownership. So what I would hope is that eventually we would have some higher level language primitives for application programmers to be able to express what they want to do, or and then for the compiler or the LibOS to take care of it, right?
One thing I might chime in is that when it comes to specifically like Rust and buffer management, I know it's kind of like an open problem that people are still working on for how to safely integrate with IOU-Ring with Linux, right? Like, I think they run into very similar problems where the kernel wants to take ownership of a buffer for some unspecified period of time and then potentially return that to the application. So that's stuff that we are also thinking about as well.
By the way, Sujay is
that's a comment that I was looking for.
Sujay is the main catnip developer. I don't know Rust, but Sujay has been doing Rust hacking for the past 8 years at Dropbox. He rewrote like their entire sync engine in Rust. And so, he's definitely, if you have Rust questions, and especially questions about catnip, he's the person to actually ask.
On the team that rewrote the entire thing.
Yeah, we did our thing in Rust too, but the question is, even mapping Rust memory model to this stuff, does it make that still easier, right? It's always a tough thing, but cool. This is awesome, and thank you, Sujay, for joining us as well, and thank you, Irene, for killing it with an awesome talk. The cat still didn't do anything during the questions.
No, he's still
I think that's all the questions we have from the audience. If you haven't yet, donate to USENIX. The cat was going to say, please donate. Please donate.
Oh, yeah. Here.
Please donate.
I'm very confused. Max says you should donate to USENIX.
We all say, please donate. Thanks for putting the link out there, Darren. And thank you, Irene. Thank you, Dan, who was on earlier. Thank you to the panel. Thank you to Adrian. Thank you to Jeff. To everybody who put this together, to obviously Camille and Hakeem at USENIX and Casey at USENIX and everybody who made this work. So open access is big. If it's hard to read papers, if you can't easily access them, that is a big deal. And of course, all the conferences. I think we mentioned earlier, OSDI being every year. It's like a really cool thing. And to have more workshops, more interesting things that we can look at, edge computing, to look at all the OS papers out there, everything like that. So thank you, everybody. I think that's it. I think that's a wrap on the show. Thank you all.
Yeah.
Later, everybody.